Question 2. I'm not going to read through all of this because it's probably going to take maybe a minute, 30 seconds, but it's just going to be a waste of time. But the question says calculate an experimental value for the enthalpy of combustion of methanol. So what we're trying to find is delta H. And you do need to know this equation off by heart. It's really important, especially when it's like more than 2 marks for these type of calculating enthalpy of combustion. It gets tricky. So we need to know that delta H is equal to Q divided by moles. That's really imperative to learn off by heart. And then also the other one, Q equals MC delta T. That's a classic one. But this one is not talked about that much compared to this one. And obviously the other one, moles equals mass over m1. Now I have all the equations that I can possibly need. I'm not going to need any more than this. So now let's work out what we're trying to find. We're trying to find delta H. In order to find out delta H, we need to find Q. So how do we find Q? Well, Q is M, and M is the mass of water. Mass of water. Q, you also need to know that key thing. Q, the M is the mass of water, and for the moles, this is the mass of the alcohol or the acid. But anything else that the mass we're given, except for the mass of water, or we may be able to calculate it out, and I feel like that's what we're gonna have to do. So Q is going to be the mass of water, which is 100 grams of water. So 100 times by C, which is given in the question. C, specific heat capacity, 4.18. Times by the temperature change, 38 degrees Celsius, 38. Now, do we not, I feel like a lot of students would add 273. You're not supposed to do that. Temperature change, temperature rise, temperature change, it doesn't matter if it's in degrees or Kelvin. You're not supposed to convert it. You have to keep it like that. So we get Q equals 15,884. And here's another key thing. This is in joules. Okay, just to be a bit wary because we're going to need to do a bit of converting later on. Now the moles of the, well, what we're working with, methanol, moles of methanol. You can say alcohol, but just apply it to question moles of methanol. Is it going to be the mass of methanol, which is, oh, it's just going to be these two subtracted. So the mass of methanol is going to be 214.02 minus 212.37, which will give me 214.02 minus 212.37, 1.65 grams. And now I'm getting there. So now the moles is going to be 1.65 divided by the MR of methanol. Well, it gives us that as methanol, so it's just going to be 12 plus 3, which is 15, 15 plus 16 plus 1, so it's going to be 12 plus 3 plus 16 plus 1, which will give me 32. So divided by 32, I get the moles as 0.051565, and now the final equation, which was delta H equals Q over moles, delta H equals, well, if we read the question, all of it, it says in kilojoules per mole to power minus 1. This is in joules, so what do we have to do? We need to times this by 10 to the power minus 3, which I'll show here. So 15,584 times by 10 to the power minus 3 to convert into kilojoules, divided by the moles, which is perfectly fine, 0.051565. Just remember, delta H equals Q over moles, because a lot of the time you're going to need to use this equation, because they get, you can see here, it gets complicated. 15 884 times by 10 to the power minus 3 divided by 0.0515625, and I will get 308. I'll get delta H equals 308. And then the final part, what's the sign in the charge? Or what's the sign in the number? Well, we know the temperature rises. So if it's a temperature increase, what does that tell me? Exothermic. And so therefore what's the is it going to be positive, negative? Therefore it's going to be negative. So it's going to be minus 308 and kilojoules per mole to the power minus 1. So a lot of tiny tricks there converting between the units, remembering these equations, understanding that we because the temperature rises, it's got to be a negative symbol, etc, etc. But that's the end of question 2.1. 2.2 suggests one reason other than incomplete combustion or heat transfer to the atmosphere why the student's value for entropy of combustion of methanol is different from that in the data book. Well, we know methanol is alcohol, and so what we can talk about is the evaporation of, you could say alcohol, but it's better to just apply it to what alcohol we're working with, evaporation of methanol, because evaporation of alcohol is a very general statement. So evaporation of methanol. 2.3, the uncertainty in each of the temperature readings from the thermometer in this experiment was 0.25 degrees Celsius. This gave an overall uncertainty in the temperature rise of 0.5 degrees Celsius. Calculate the percentage of certainty for the use of the thermometer in this experiment. So we don't really care about the uncertainty in each of the temperature readings. We care really about the overall uncertainty, which is this. So percentage of uncertainty is going to be the overall uncertainty divided by our reading, or our total value. Well, for the use of the thermometer, well, the thermometer will give you a temperature rise of 38 degrees. So it's going to be 0.5 divided by 38 times by 100. For these type of 1 markers, percentage uncertainty, just really highlight every key detail that it wants you to do, and then work from there. Because sometimes, like, it's just the question is literally telling you what to do, but you just have to read it properly. Obviously, know the formula as well. And then 2.4, the student said correctly that using a thermometer with overall uncertainty for the temperature rise of 0.5 degrees Celsius was adequate for the experiment. Explain why the thermometer was adequate for this experiment. Idea being that temperature change / rise is a much more significant, actually is much bigger than uncertainty, or heat loss is a more significant issue. One of the two should be fine. And 2.5, enthalpy combustion is that, density is that, calculate heat energy release in kilojoules when this much ethanol is burned, give you answers appropriate number of significant figures, 3 marks. So the first thing I can see is that we've got density and we've got a volume. And what is the classic equation? Density is equal to mass over volume. So we can find out the mass of ethanol. Mass is just going to be density times by volume. So the mass. So that's the first thing. Even if you don't know what heat energy release, how do you work that out? First, just find out what values they gave you and work with that. So the mass of ethanol is just going to be 0.789 times by, now this is in dm cube, so we need to convert into centimeters cube, so we just times by 1000, so it's going to be times by 500. 0.789 times by 500, 394.5 grams. 394.5 grams. Now we've got the mass of ethanol. What also can I work out? That is not going to take that long. The moles of ethanol. The moles of ethanol. How do you work that out? It's just going to be the mass, which we worked out, 394.5, divided by the MR of ethanol, which is, ethanol is that. So it's going to be 12 for carbon, plus 3 hydrogens, plus 12, plus 2, plus 16, plus 1, 46, divided by 46. That will give me 8.58. 8.58. And now for the final mark and the final step, all we have to do is find out the heat energy released. Heat energy released. All we're going to do is going to do the moles. 8.58. 8.58 times by the enthalpy of combustion of ethanol, which is 1371. We're not going to include the negative symbol because that just tells me that the reaction is exothermic, the temperature increases, but we're not going to use the negative symbol in the equation to find out the heat energy release. So 8.58 times by 1371, 11763, we'll say 11,800 kilojoules. And that is the end of question 2.